Hello, welcome back to another lecture. In this lecture, we're going to go ahead and design a curved glulam beam. Take a look at those pictures. I mean, these beams are really majestic. They are beautiful. So we're going to design one of these beams. Let's go over, take a look at the example we have that we want to design it. First, we're going to size it, and after we're going to size it, we're going to go ahead and run through all the stresses, see if the size we selected is okay. And here the roof beam on a design is about 40 feet beam, and the loading is 780 pounds per foot, which is basically dead load plus snow load. The radius I'm looking for is 75, and if you're looking for more radius, the manufacturer has a good recommendation on radius, and there's an equation there for it. Anyway, let's go ahead and start. To size a beam, really, a lot of time it's basically trial error. You come up with the size, and you go ahead and see if you oversize it or undersize it. But to make an educated guess, what we're going to do, if you look at the table 5.31, you have the bending stress equal FB times CD, CM, CT, CL, CV, CFU, CC, and CI. Not all of these are going to apply because of the condition you have for the inside door. So we just, some of them are going to be unit, especially like CL is a roof beam, has a lateral support, so they become unit. And then we're going to worry about curve factor, size factor, CT, CM, which is basically 1, and CD because has a snow load is 115, and you can look up the spec section 2.315. But at the beginning, you want to size the beam. We got to guess as these two because we don't know the size. These are based on the size and based on some calculation, which take time. And the best guess is for those 0.9 to 0.99 or even 1. So let's say 0.95. I'm going to just guess at it for here. And let's go ahead and say FB prime is equal, how about this one? FB prime X is equal, this is from table 5.3.1, and we're going to go ahead into table 5A. So from the table, we're going to go ahead and look up the FBX, which comes out to, I had it here a second ago, 2400. And CD is 1.15, and the other one is 1. Let's guess at 0.95 and 0.95. I'm just guessing at these. So my F prime BX, this is just a guess, it's not the actual value, and that comes out to 2491 psi. Okay, now I would like to find out what is my bending moment, maximum bending moment for this loading. And you know that's from the beam formula, that's WL squared divided by 8, that's maximum moment, and that comes out to 780 times 40 squared divided by 8, and that comes out to 156,000 foot-pound, but I don't need that, I want an inch. So let's convert that to an inch, and that become 156,000 times 8 become times 12. I mean, become 187,000. No, am I right? Yeah. 1, 2, 3. Yeah, 1.87. Yeah. So that become that, and then now we have that. So my section modulus, it comes out to this number, which is the maximum moment, divided by F prime B X, which comes out to 1872000. Divide that by 2491, and I get 751 inch cube. Now, if I go into table 1D and 1C, from table 1D and 1C, I can go ahead and find the section modulus and size my beam. And of course, with this 751, you can find out variety sizes that will fit. So how are we going to size this? If you look at your beam, say this is your beam, you need to have a desired width and desired height. And from all those that I have, I'm going to go ahead, okay, because I want to make sure my width is 6 3/4, I'm going to go with that. And then I'm going to use 26 by 1/8 for my height. Okay, now I have my size selected, then I can go ahead, calculate all my stress to find out if this size is working. Okay, the first thing I'm going to look for right now is a curvature. I want to find CV. Let's calculate CV. I want to go different color here. Hold on. CV. Okay, let's calculate CV, and that is from table 5.3.6. 5.3.6, and that is 21 divided by L by power of 1 over X, and multiply that by 12 over D by power 1 over X, and multiply that 5.125 by power divided by B by power of 1 over X, and that should be less than 1. If it's more than 1, then we're going to use 1. So less than or equal. So if we're going to continue, plug in those numbers, and if you take a look at the what we have on I have on a board based on NDS 5.36, our X comes out to, since we're using Southern Pine, our X is kind of 1 over 20. So go ahead and just plug in, and our L between the maximum moment is between the moment where the moment is 0, which is basically the reaction, comes out to be 40 feet, and B and D we already selected is going to be that, and we're going to calculate that, see what's going to come out. So CV is going to come out. I'm going to erase this since I don't need this anymore. CV is going to come out equal 21 divided by 40 by power of 1 over 20, and time 12 divided by 26 and 0.125 by power 1 over 20, and 5.125 by power divided by 6 and 0.75. 1 over 20, and I get 0.919. Okay, so now we found that. Let's go calculate CC. We want to get CC, and that is from equation curvature is section 5.3.3. Yeah, that's what it is. And that's equal 1 minus 2000. If you take a look at that section, it's time T divided by R. The whole thing is squared. And I have room here, so I'm going to say 1 minus 2000 time. Now the thickness is the different lamination, and when we go to Southern Pine, that is 1 inch and 0.375, 1 and 3/8, and divide that by our radius was 40 times 12 is 900, so radius is equal 75 feet, which is equal 900 inch. So time divided by 900, which is a radius, and square that, and that comes out to 0.995. Okay. Now we have found this factor and this factor. Let's find out really what the actual FBX is. And here we guessed at it, and we came up with this number to size this. Now let's find out the actual value. So now we have the actual value. Let me go to switch color again. Let's go back to green. So the actual value comes out to FB prime BX, and that is we already have those, which was 2400, and that's from previous step. We know that's 2400, and CD, and that's 115, and CM and CT is going to be 1 really, and CV was 0.919 and 0.995. That comes out to 2520 psi. So now we have got that. Let's find out the other stresses, like let's find the shear stress, and this is again from table 5.31. We look at that table, we can calculate all this stuff. Let me take this out of the way here. So we're going to find the shear stress, which is F prime Vx, and that's from the same table that we have, table 5.3, which is F of Vx multiplied by CD, CM, CT, and CVR. To find CVR, we can look at the section, to find this right here, look at 5.3, which I'm going to put on a board, 10, okay, and that is, comes out to, based on same table that we have, F of Vx comes out to 300 psi, and multiply that by 115 and 1 and 1, which gonna comes out to, oh wait a minute, CVR, and that comes out to 0.72. 0.72. Now we have 248 psi. All right, so now I have calculated all that. The next stress I want to calculate is the modular of elasticity E prime X. So E prime X, based on the same table, is EX time only CM and CT, which they both 1, so basically comes out to 1.8 million psi. So let's calculate the radial stress, which is F prime RT, and that's equal FRT, and an adjustment factor is on a table, CDCM and CT. However, to calculate FRT based on 5.28 in DS 5.28, okay, and that comes out to F prime RT is equal to the equation I have for it is F of Vx time CVR divided by 3, then we have the CDCMCT. CDCMCT, and that's from the section 5.2.8. And then if you plug it in, it's going to come out to 300. We know that it's a 0.72 from here, and divide that by 3, multiply by 1.15, and multiply by 1 and 1, and that comes out to 82.8 psi. Okay. Then we have our maximum moment, which we already calculated was 187,000. Okay, so we know that. So let's write down all these stresses. It's someplace in the corner here, so I have it, because I need them. Okay, all my stresses is going to be, let me use a different color here. So I had boom, 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 f p prime x, f prime bx, that came out to 2520, and f of prime vx, that came out to 248. And then the next one was e prime x, came out to, that didn't change really, 1.8 times 10 by power 6, and f prime RT come out to 82.8 psi. I think I got everything FRT, so I gotta write these down. Because I'm gonna erase this board. I need space. 1, 2, 3. Now we got all stresses. We have our maximum moment, which is at 156,000 foot-pound, or just make it inch-pound, which become 1,872,000 psi, no, inch-pound. And another thing I want to find out, I would like to find out the mid-depth radius. What's the mid-depth radius is going to be? So they call that RM, and RM is equal R plus D divided by 2, and R came out to 900 inches, 75 feet or 900 inches, and divide that by this 900. If you don't know where it came from, it's basically, let me just clarify that equal 75 feet times 12 to make it feet from to an inch, and divide that by plus D. D was 26 and 18.125, divide that by 2, and so RM comes out to 913.1. Okay, that's inch. That's correct. So now we're going to go ahead and come back up here again. Let me start out with blue, and we're going to calculate the radial tension stress, and the formula for that, FRT is equal 3m, divide that by 2rm BD. And if you look on the board, that's where it come from. And that's from a section 5.4.1. 5.4.1. And let's plug in the number. So we have maximum moment came out to 1,000,003 times 1,872,000, and divided by 2 times radius, which was 2 times RM, 913.1. And BD, B is 6.375, no, 6.75, and D is 26.125. That comes out to, so FRT, I get 17.4 psi, and that is less than 82. So it's less than 82.8. That checks out. That's good. Now let's do the bending, which that's how we sized our beam. We're going to do the same thing over again. The bending is going to be, if you remember, there is a formula for bending. So F of Bx is equal 6m divided by BD squared, or we can just say use the section modules. That's the same thing too, doesn't matter. M divided by S, or you can do it this way. We have the size, and that's going to be 6 times. Let me change marker. I don't like this marker. 6 times 1,872,000 and divide that by B 6.75, 26.125 square equal. What do I have? What do I have? We can do this M divided by S, which we know the S for this came out to, I don't know. I have to look up the chart what S was. That comes out to 2440. 2440 is that less than 2520. Just made it. Check. So we checked this one, we checked this one, we made the bending, we made the radial stress. Let's keep on going down the charts and can make sure we get all of them. Okay, let's check for shear stress. Shear is, go back to green. V for these shear is going to be the maximum at the reaction, so I'm going to have one right here and one right here, and V is equal usually WL divided by 2 because it's even, so half and half on this side. So that's come out to, let's write it here. So V is equal WL divided by 2, 780 times 40 divided by 2. I have, what do I have? 15,600. 15,600 pound. And now we want to find out the shear stress. The shear stress is going to be F of V, which is equal 3 over 2 or 1 over is 3V divided by 2BD, and that's 3 times 15,600 divided by B 6 3/4 multiplied by 26 1/8, which is 125. So I get, what do I get? I get 133 pound PSI. 133 PSI, and that is less than 248. Check. Okay, so we got that, and in here, let's check for deflection. The problem which I put on the board ahead of a time is not really the deflection both for combined for the dead load and snow. The deflection should not be, those are design criteria. So in our design criteria, the deflection is, what do I write? What do I write? Right here, deflection was given at 2.7, I believe. Look at the problem. Yeah, deflection was 2.7 inches. That's what our design criteria is. So now we're going to calculate deflection to make sure we're not going to exceed that. I'm going to go ahead and use right here. Let's make room for me so I can calculate the deflection. Okay, so the deflection is we know the equation from the beam formula. Delta is equal, actually you can go to section 5.4, hold on, let me write this down. 5WL by power 4 divided by 384 E prime X IX. Or we can just say from the section 5.4, 5.4-4, we can write 5W L4, divide that by 32 E EX BD cube. That's not good. BD cube. So if I plug in those numbers, my delta comes out to 5 times 780 times 40 feet by power 4 by power 4, and if we convert that, it's going to be time 1728, that's inch cube by cubic feet. That's just a conversion, because I still have I'm going to divide by 1 by 4 over here, so I don't have to convert all 4 of them, and divide that by 32 times 1.8, 10 by power 6, and time BD 6.75, and time 26,125. So my delta is coming out to 2.5 inches, and that is less than 2.7. Deflection checked out. All right. So there's one more thing we're going to check out, and this is kind of a little bit different, has a twist to it. Give me a second. Let me erase this story, and we'll tell you how we're going to do that. Because we have a curved beam, in a curved beam, we're going to worry about horizontal displacement. So you have something curved, and you push a weight on it, it kind of pull out a little bit. So how much this horizontal displacement is going to be? We got to calculate that. That's important. And there was a lot of equations out there, and good luck looking for them. I give you some recommendation where they come from, and we can go ahead and calculate these horizontal equation. First is it's given by this equation: delta H is equal 2H delta C, and divide that by L. Okay, we don't know what H is. To calculate H, there are 2 different ways we can do it. One way is H is given by this formula. This is from the old code, I believe. Let me see if I can bring it up. And some places call them H, some places call them C, and depending how you're going to see it. And that's equal radius minus 4 r squared minus L squared divided by 2. And if we plug that in, it's become 900 inch, we know that, minus a square root of 4 times 900 squared minus the L was 40 feet, which is same as 40 feet times 12 is 480 inch. And divide by 2, it comes out to, what do I have? 32.6. Okay. And there's another equation that I found. There's one on NDS, which I don't like, and you can see right there, I'm not going to even bother using it. And there's one from manufacturer website, which I kind of found I liked a lot. A lot of people uses that, and that is they given this equation. Let me write it in a different color. It's given this equation: R is equal L squared divided by 8C. Now C is same as the H here. So if I can go ahead and C comes out to L squared divided by 8R, and let's see what we get from this equation. So that's 480 squared divided by 8 times 900, and that comes out to 32 inches. Not much difference. Delta H comes out to 2 times 32, let's do this one, doesn't matter, 0.6. And you can see that it's not going to be different. Time delta C, and our delta C was 2.5 inches. We calculated someplace 2.5 inches, and I erased it, and divided by L, and L is 480 inch. So that comes out to 2 times 32.6 times, yeah, that's right, 0.34. Not much, just a little bit under half an inch. So what does it say? And it says when we put this weight on here, that's going to move out about 0.34 inches. If you fix one end and make it movable the other end, that's okay. Or you can split it between both two if you have a move. You can depend on you how you're going to do your support reaction. Okay, I hope you like this. I hope it was good. I hope it was